It's really encouraging to get an applause before I even said a word. So thank you very much. I should say I'm very happy to be here today, and I very much appreciate the invitation. I wouldn't come to the conference, to the Complex Systems Conference, which is running from Monday on, if not because I got an invitation from the Young Researcher Society community, wherever you call it. And I think it's really an opportunity to tell you about some stories that you may not have heard of ever, right? Because I know that you have arrived to complex systems in the data age, right? So most of you, or many of you at least, work with data. And yes, complex systems is about data, but data is recent, right? So this large amounts of data that we are getting in our times is not something that was there when I started working on the topic, right? So I want to give you some background of how the field developed, starting in the late 80s, right? You were not born, right? Most of you, I think that all of you were not born at that time. Okay, so as Maria said, I have a background in physics, but I've been always interested in biology. Actually, even at the time that when I had to choose when going to the university between physics and biology, it was really unclear to me what to choose. So I went for what I considered to be the hardest science, in the belief that maybe I could learn biology in a more easy way than physics. Yeah. So I think that this turned true, but eventually I succeeded in mixing both interests. Actually, so Marta was telling that she didn't know that she wanted to be a scientist. I did know since I was 5 that I wanted to be a scientist. I mean, my passion absolutely was nature. So I didn't have my socks in my shelves at home. So they were all hidden somewhere, and I had butterflies, I had worms, I had insects, I had something to look at the stars, maps of stars, and so on. I knew I wanted to be a naturalist. Right? So this was my passion since I was very young, and somehow this makes things easy because you don't have to decide. So there was this feeling coming from the guts, really, not even the heart, it was the guts, right? And this has signaled my way, all the decisions I have had to make. And none of them was guided by, say, the decision of, will I get my income from what I do? Will I be successful? So I've always thought of enjoying, right? So I'm enjoying, I have enjoyed for 30 years since I started in complex systems, and I am enjoying today. And I don't know, I think that this enthusiasm moves the word and should be also a main motivation when you choose, right? Okay, so with this preamble, let's go to the history. You see, it was very funny because I've seen some of the slides, so some of Marta's slides, and I thought, wow, we have some convergence in some topics. So you will see some repetition of stories, but I'll give you a very personal viewpoint on all these stories. So what's complex systems about? Complex systems is about patterns, and it's about processes. When you look at these birds and you see the amazing forms they make in the skies, and you know there is no guide, there is no one telling them to fly in one or another way, to organize as a flock. There is no central intelligence, say, that tells them how they have to move, what kind of patterns they have to make. And this is what, when you observe nature, really puzzles you. Right? So I think that this is also for me is observing a pattern and not having an explanation for the pattern is something that really is a challenge, is a real challenge. So how do these birds work? How do they organize? What are the interactions there? How now we have heard, all of us have heard about interactions, about emergent properties, and about all this stuff, right? But many years ago, this was still sort of a mystery of how they organize. But you have also those jokes, right? Or you see that the birds flying in a V shape, in a V formation. And you see, why is the first one sitting there? Well, because it has the map, right? So no, there is no map. So they self-organize to have these shapes, right? So complex systems is about patterns. It's about processes, and this has been a motto for the field since very early. I have here some examples of different studies of different topics that fall under the complex systems paradigm, right? You have people clapping in a stadium. Somehow they manage to synchronize, even if the distance there is between one side and the other of the stadium is so long that it takes a while for the sound to propagate from one side to another, right? But still, they still synchronize. You have brain activity. So we know more and more about how the brain works and how these patterns turn into interpretations of the world. Right? So there is now much neuroscience, also moved by data, but also moved by the attempt to understand what are the processes that make sense of the outer world. You see formation of urban areas, of cities, of urban settlements. So this is not something random. You see some order there. You have stripes in zebras or so the skin of animals. This is an old problem in mathematical biology. You have ants. Also, there is no central intelligence if you may have a queen. So the queen is not ordering what ants have to do and so each ant has to do something. No, there is self-organization in the system. This is a classical example. This is the Belousov-Zhabotinsky reaction, right, which causes chemical waves, spiral waves in the pattern. Okay, and several others. So this has been extended to something like economic systems and to hard biological problems like virus evolution, genome evolution, and so on. So my field is more, so my technical part, what I know is modeling, and modeling in particular in biological systems, right? But I've been going a long way since I started. So I want to tell you a bit about the history of patterns, how humankind looked at patterns since very early, and how the wish was to make sense of these patterns, right? Do you recognize what's here? Yeah, someone can name it? Epicycles. Yeah, right, epicycles. This is the epicycle. So the early descriptions of the skies, and this is one contact with what Marta said, was like trying to make sense of this retrograde movement of planets, right? And it was very difficult to explain. So they invented this sort of mechanistic explanation, which was not purely satisfactory, but actually could somehow take into account the fact that in the skies you see planets that go backwards and they move forward and go backwards and so on, right? Indeed, and to come Kepler. Kepler is one of my most favorite scientists of all times. Yeah. So it's true that he was using Tycho Brahe, however it is pronounced, who was born in Denmark, in the Kingdom of Denmark at the time, right? Now belongs to Sweden, where he was born, but he was Denmark at the time. And he had all sorts of data, and then Johannes Kepler tried to make sense of those data. Kepler was the fifth son of a very poor family, and his mother was almost burnt because of witchery. So he had a very difficult life, so nothing to do with Galileo, who never responded his letters. I think that Galileo was a very mean reviewer, and Kepler for me was really a hero fighting against everything just to try to make sense of that. So he behaved as the machine scientist of the time and derived the laws that we know with his name about the movement of the planets. Still, this was pattern. This was not yet process. And the process was due to Newton, indeed, right? Who much later could derive the laws, the essential laws of planetary movement. And once you have the laws, you can describe any pattern related to or arising, emerging from these forces, right? So even at that time, I see there the signature of complex systems, and Marta has also used this example, that's amazing, where you go from pattern to process and to mechanism. So what we love to do is try eventually to find the mechanisms that make sense of the patterns we see in the world, right? Okay, so that was so far so good for the movement of two bodies, right? You had the sun in the middle, and you have these orbits, elliptic orbits described by Kepler, and then you have gravitations that takes into account this movement. But what happens if you have more than two bodies? Then problems arise, because the three-body problem is not the two-body problem. As you know, two-body problem is exactly solvable with these elliptical functions, but the three-body problem is not solvable. So some very motivated people in the end of the 19th century. This is King Oscar of Sweden. For his 60th anniversary, you can see there are some differences with the kind of royal families we have nowadays. So he was very well, so he had a background in mathematics, was very interested in mathematics. And for his birthday, said, well, I'll give a prize to the person solving the three-body problem. Right? Excellent. Who was there around? Poincaré. Poincaré was a very brilliant mathematician of the time, was a personal friend of the king as well. So there was already some understanding that he would be working on the problem when he would be saying that there would be a prize for this person. And so he started working in the three-body problem. And he found something that represented a change of paradigm in the dynamics of systems as it was known before, right? This is a draw that is original from Poincaré. Do you recognize what's there? No. Someone? Yep. No. Again? Sort of. It's a, yeah. No. These are count totals for Kolmogorov, Arnold, and Moser, who were three people studying deterministic chaos. Right? What this found is that when you have deterministic chaos and non-dissipative chaos, like in the solar system, because dissipation doesn't enter gravitational equations, then you have your phase space is broken into torus that are one inside another in a fractal shape, one inside of another, and you have the orbits going in between the torus, the solutions of the system, right? So this is what Poincaré realized, and he realized that there were infinitely many crossing points. So this was cut and divided, cut and divided, and cut and divided again and again. And he realized that there were no periodic orbits. That was really a crazy discovery, right? So it was, there are non-periodic orbits that neither grow indefinitely nor converge to a fixed point. And this was something that no one had ever heard about before. This is, you can find it in the Wikipedia. This is the three-body problems for three masses of equal mass, three bodies of equal mass. And the center of mass is depicted in the middle, and you see the trajectories of the three bodies here for a very short time interval, right? So you see these apparently disordered trajectories, but this is just the signature of chaos, right? So Poincaré was the first discoverer of dynamical chaos in conservative systems. They also described some periodic orbits which are unstable because they would sit just on the separations between these camp torus, right? And you would have the three bodies moving there, but any perturbation would kick them away and throw them into a strange attractor, into a non-periodic orbit, right? But this is another representation of this torus. Now a more modern one. Wow, doesn't matter. And this was the work that Poincaré presented to the prize, and he got the prize even if he didn't solve the problem, right? So the advances in mathematics and in the understanding of the physics of the three-body problems were so big that, well, he got the prize and changed the paradigm that we had at the time, right? Please interrupt me at any point, right? And ask whatever you feel you want to know about, right? Okay, so, what's that? Have I missed? No, okay. So one important point of chaos, which was actually the first part of complex systems that I got in contact with, was this sensitivity to initial conditions that I presume all of you have heard about. Yeah? Someone doesn't know what sensitivity to initial conditions? How many of you are not physicists? Okay, which areas do you come from? Yeah? Maths? Everyone? Or something else? Finance. Okay, good. So, okay, because I'm going to talk about physics in a, say, popular science way in some cases, but I hope you also can follow me, right? So otherwise, just interrupt me and ask. So this sensitivity to initial conditions, as you know, is the fact that you start with two initial conditions and they can be arbitrarily close, but eventually they diverge, And the person who first saw this sensitivity, which is an intrinsic characteristic of chaos, was Edward Lorenz. And here comes the flap of the butterfly. You have heard about the metaphor, right? There is a butterfly flapping the wings in Texas, and you have a tornado in Australia, somewhere else. So Edward Lorenz was, was studying weather, actually not climate, weather. And he was very interested in these convection cells, these ferret cells that are formed in the atmosphere. And he decided at a time where this was not common to make a simple model of how these cells were working. And this is Lorentz model. That is also something that everyone in complex systems should know about, because this is a paradigm of chaos in modern times, of modern chaos. So he had this very apparently simple three equations where it was describing the rate of convection, the horizontal temperature variation, and the vertical temperature variation, right? Okay, in both sides. And what he found was that actually there was this sensitivity to initial condition and this non-repetition of patterns, even if you started with very near points in phase space. Right? This is the famous Lorentz attractor that you know that also resembles a butterfly. And these are two runs where you can see how two conditions which are apparently very close, you see there are the differences, so eventually separate and go into different trajectories, right? So this was a real breakthrough, but this was somehow a computational rediscovery of what Poincaré already knew, right? So every time we have a new technology, we can go into exploring areas or ways of looking at systems that we were not able to do before, right? Of course, Poincaré couldn't go much farther. Has any of you studied mathematics of chaos? Good. And you know it's very hard. I mean, it's as a system. So to visualize with mathematics what's going on. So either you are very talented, or it's very difficult to imagine that you have this sort of dynamics there, right? So, but then you have a computer and you input these very simple three nonlinear equations and you get these complex dynamics, right? Okay, so the problem with this sensitivity to initial conditions, as in the example of Lorentz model, is unpredictability. You cannot tell what's going to happen in a temporal horizon, certain time in the future. Right? There is a mathematical formalism to explain that, and it's usually caught in what's called the Lyapunov exponent, that lambda there, another exponential, different exponential. That's not an energy, but it's a sort of measure of divergence, because you have time. So 1 over lambda is a sort of the time at which you can make prediction, and after 1 over lambda, essentially your predictability is lost because your trajectories have diverged. You can do it a bit better with some techniques that have been developed more recently, but actually you cannot go much farther than 10 times 1 over lambda. So there is a horizon for predictability, and it's not possible to go farther. Okay, I mean, of course, one impossibility of predicting is the fact that you cannot measure with infinite accuracy all the states of the atmosphere, right? And this is, I mean, by definition, even if so prediction of weather has improved very much, this is not something that we are going to achieve ever. Right? So Lorentz liked to say that chaos is when the present determines the future, but the approximate present does not approximately determine the future. Right? So it's deterministic, but since you cannot measure with infinite accuracy, you cannot predict for a too long time. Lorentz also changed our view of what dynamical systems were. This, at least it made it popular. So Poincaré probably had visualized it, but many people, so it was not layman knowledge that there was this sensitivity. And Lorentz made it popular in a way. Right? So received several acknowledgements for that. And I like just to know that he received the Crawford Prize, which is also given by the Royal Academy of Sciences, for fields that are not included in the Nobel. So you see, here we face something that you will see, so again and again, and hopefully not that much in your future than it was in my past looking at my future, which is the classification of knowledge in compartmentalized sciences, right? You have areas. So weather prediction is not something that deserves a Nobel Prize. Something else, right? It's important, but yeah, it cannot be included in a Nobel Prize. And also, if you do science in other disciplines, you might find people that believe that you are not an economist, not a physicist, not a biologist, not a physicist, so you are out of any community. And I feel you can feel at home here. I hope you can feel at home, because that has been a constant. And this is a parenthesis, but this also has to do with what you do when you are making transdisciplinary science and you want to publish in journals. Now, situation is not that bad because there are journals which are in between, right, generalists, but it was very bad in the past. Okay, anyway, so at that time, it was in the 90s already of the 20th century. Still, he didn't get the Nobel Prize because it was not something that that was considered as in the novel areas. But the committee said, does he make his boldest scientific achievement in discovering deterministic chaos, a principle which has profoundly influenced a wide range of basic sciences and brought about one of the most dramatic changes in mankind's view of nature since Isaac Newton. Can figure out. So his discoveries are recognized at the level of Newton in the change of paradigm, but were not acknowledged so high. These are the kind of books that I was reading when I started in studying what was already at the time was called complex systems, but it had more to do with chaos actually. There was this very nice book of James Gleick that I read in 1988. So when I was first exposed to chaos theory. So right after it was published, there was this deterministic chaos, which had somehow not so difficult mathematics of chaos. It was also very nice. There was Prigogine, one of the forefathers also of these ideas, with this order out of chaos. Actually, with Prigogine, reading Prigogine was the first time that I realized why there is no time reversibility and the contribution that entropy makes to this non-reversibility of dynamics. So it was very interesting read. And something like the fractal geometry of nature by Benoit Mandelbrot, that, well, it was also very linked to this self-similarity, to this repetition of patterns and the ideas of self-organization and so on. Right, so. Actually, last year, and again, Marta also mentioned that, there was the Nobel Prize to 3 people, and 2 of those people were related to climate, right? So there was this weather that Lawrence said is not predictable, and we have experienced it. We experience it every weekend, right? You make your plans and you wait until the last day possible to decide what you are going to do, because you know that the prediction is not always reliable. On Monday, you cannot believe what's going to happen on Sunday, definitely. So, but still, climate is something different. So this person, Syukuro Manabe, was the first person to devise a model for climate, which is, as I was saying, different from predicting weather, right? So he was concerned about the relationship, about radiative balance in the atmosphere. So there are some mechanisms to lose heat and to produce heat and to accumulate heat on Earth, right? And this balance is what he was looking at. And well, he included different aspects, but in a simplified way. And it was one of the first models, and he had some predictions. And these predictions had to do with the greenhouse effect and CO2. But he saw that increases in CO2, which was a gas that was not included in previous models. So people were considering water, because it's a powerful, also water is a powerful greenhouse effect gas. But he considered also CO2. And he saw that there were some effects of this CO2, that if you got some decreases in temperature when you were diminishing the levels of CO2, but it was not symmetrical when you increase the temperature due to increases in CO2. Right? So actually, this paper of him was selected as one of the most influential publications of climate change ever. right? So this was a sort of prediction. And later, the other Nobel Prize awardee, Klaus Hasselmann, demonstrated that you could distinguish between the long-term climate evolution and the rapid and chaotic short-term oscillations. You see, this is an integration of these variations that do not allow you to predict when we talk about weather, but when you consider the Earth as a whole, there are some things that you can say about the future of climate, about the change in temperature and so on. So this is, you're integrating all over your system somehow, and you can see some trends, some long-term trends that are not in this small-scale variation. So Klaus Hasselmann was demonstrating this, and on top of that, he could see that the variations in the CO2, so you could distinguish what were natural variations and which variations were due to the effect, so to the action of man, right, of humankind, right? And this is altogether what was the Nobel Prize. And this is, of course, a recognition that this science of very complex systems with many elements, with many interactions, and with emerging properties and so on, this is good science, and this is a science that deserves a Nobel Prize. So, and I like this also especially because Lawrence was out of these areas. So things have changed. The way of thinking about complex systems has changed. And now this is something that people acknowledge as a solid, sound science, and something that is really telling, with consequences that I mean, you have to believe, you can believe that's solid science, right? Okay, anyway, what's a complex system? I should have not put the definition here. When you think of a complex system, do you have always, all of you have a clear idea what a complex system is? Of course you work with complex systems, with complicated systems, with entangled systems, with many ingredients, right? But it's not something that is extremely easy to define. Among the definitions that are there, the one that I think I prefer is the one given by the Santa Fe Institute in New Mexico. Right? It's a system where many agents interact and adapt to each other and to their environments. Right? So there are several keywords here, right? You have many agents, you have interactions, so you have no supervision. And there is an adaptation in the system, so an evolution towards being fitted to a given environment. Right? That's very evolutionary, actually. So that reminds very much of biological systems. But of course, this also works for social systems and for many others that, so for chemical systems with interactions and so on, right? So you have here some examples. And another important point is that you have some surprising emerging properties at a level that transcends these agents, these individuals in the system, right? Anyway, there is no consensus on what complex system science is. And I have this book, for instance, which is called 43 Visions for Complexity. So every scientist has a different view of what complexity is. And I'll give you just 2 examples, right? And I'm sure in your fields, you have different views of what complexity is. So this person is Stuart Kauffman. He's the author of a well-known book also in the 80s, which is At Home in the Universe. And he was, at that time, he was wondering, how is it possible that you have the emergence of complex chemical systems in a pool of molecules, of chemical molecules with no complexity from scratch, right? So how does this complexity emerge? And this is his answer, to my surprise, actually. He says, there is no science of complexity. What we have is a fairly well-developed set of tools for examining various complex adaptive systems. Do you agree with that? Do you think there is some truth here? Or that's a difficult question. I don't know. I really don't like to see science in methods. Methods are a tool to answering questions. All right? I hope you have questions to solve and not just methods to develop. Right? It's also important. No, I mean, no controversy at that. So some people have to be developing tools, but as a science, complexity as a science, to be seen just as a box of methods, I think it's a bit of a, to my surprise, because he's a person that I mean was very much involved in also in the Santa Fe Institute and in complexity, as I understand it. So, but this was his definition. And here we have another definition from someone that I very much respect also, Peter Schuster. And he says, defining complexity is very difficult, if not downright impossible. That's somehow like defining life. Have you seen any serious and reliable definition of life? That's also, there is a whole body of people working with that. A good working hypothesis might be, everything that is not simple is complex. Wow, come on. In this way, we define nonlinear behavior. Systems are complex for different reasons. Because of our lack of understanding, and he gives us an example, the solar system, when you don't know the rules, you don't know the mechanism, it's very different to make sense of what you are seeing. Because of the lack of method, for instance, you see particle formation or chaos, and you don't have methods even to measure, to accurately, to measure, to quantitatively characterize the patterns you're seeing, or because it's an inherent property of the system. So for instance, you have reactions inside the cell, and the best descriptions of metabolism, you may know, are thousands of rate equations where you have all reactions going on, and they're very good at predicting how the cell will change if you change, for instance, the sources of nutrients. But in my view, it lacks an understanding of what's going on. So this is a kind of models that are very good at predicting, but are not that good at explaining. So these are two different approaches that you can also take when you deal with a system, right? So this is still something that is not so well defined, right? Although, as I was saying, I very much prefer the definition of the Santa Fe Institute. Okay, so last year in Lyon, there was someone presenting this summary. I really miss the pointer, I have to tell you. Right? This summary of modern complexity. You have here a time scale. Can you see? You cannot see it even. Oh, my God. Okay. Okay, so you have there the 80s at the beginning, and there is a timeline. And here you have different topics that you cannot read, but I will tell you a little bit how this goes. You see there at the beginning, chaos and physics. Right, so everything started with chaos, this modern, I mean, I have nothing to do with this person. This was someone just looking at publications for keywords and making a phylogeny of different areas in complex systems. So you see the explosion when we go into the 21st century, right? But early on, we had chaos. We had chaos, we had physics, and we had complex adaptive systems, which is the second group here. Cellular automata, which were also very popular at the time, dynamics, adaptation, evolution, nonlinear processes, and then you come here with biology, interaction, networks. Networks explode at some point, right? There is an explosion in a study of networks. Now, there is no one doing complex systems that cannot say something about complex networks, right? This is also a must, something that you need to know, because this is a very powerful description of many of the things that we see. And then you have all sorts of other areas. Complex network, what's that? I cannot read it there. Complex network analysis, yeah, again, DNA molecules, phenotypes, control strategy, network dynamics, community structure. There is a whole block here. All this here is community structure, and so on. And I mean, we can name more. We have econophysics, we have social sciences. So everywhere where you have these many agents distributed, and now, thank you again to the large amount of data we have, so we can face the study of these systems from a perspective that was not possible before. As you see how this explosion has gone, right? So at the beginning there were this more simple in a way, or more so localized areas of knowledge. Here, everywhere, you have also some views like fractals, self-similarity, power laws, and so on, and something that I have not mentioned, and I don't know even if it's here, which is self-organized criticality. Who has heard about self-organized criticality? Yeah, of course. Yeah, okay, good, good. In the timeline, we have here some highlights. The Santa Fe Institute which for a long time was a reference, a world reference for complex systems, was grounded in 1984, right? The Max Planck Institute for the Physics of Complex Systems in 1992, right? Much later came the Complex Systems Society. The Conference on Complex Systems was first celebrated in the year 2004. So some had been working on complex systems for over 20 years. And the IFISC, our host in this occasion, was grounded on 2007, right? So there's some order in how things develop. And there has been also a significant change in understanding of what this means, right? So many people who came from different areas of physics, statistical mechanics, specifically, so very often from nonlinear physics, or physicists who were working in areas which were not pure physics, started to incorporate into complexity with time. Okay, this is a picture of my group when I started my PhD. This is 1993, about. This is Ricard Soler. He was my supervisor. He's only 6 years older than me, actually. I attended his PhD defense. And I can say that I had already started my PhD. That was crazy times, actually. So some other people in the group that you may have heard of, Jordi Basconta, who is a very well-known ecologist, now in Switzerland. Bartolo Luque, well, he's more going into mathematics and does all kinds of crazy things still. And Jordi Delgado, he was the computer scientist. So Jordi was a biologist, Ricard was both a biologist and a physicist. I was a physicist and Bartolo was also a physicist, but we were already a transversal group. And this was started essentially in 1990. So the first time that I heard about all this stuff was when Ricard was delivering a series of talks at the Facultad de Informática, so computer science faculty in Barcelona, and I was attending the talks because at the same time I was reading James Gleick's book, Chaos. And I thought, wow, someone talking about chaos, I have to go and hear it. And it was really mesmerizing. So it was incredible. So how he could convey the passion for this field. And I was still in my third year of university, and I started in the summer working with him on some nonlinear pendulums with magnetic forces and so on to, well, yeah, to get a higher mark in one of the matters in mechanics, right? So this was the beginnings, you know, I mean, we started really early, and you see the blackboard behind, right? You see bifurcation diagrams and yeah, Lyapunov exponents and so on, right? 1994, Ricard and I wrote this book, Order and Chaos in Complex Systems, while I was doing my PhD. And yeah, it was early times, and I mean, I look at it and I say, wow, so many things that it was like an explosion. Like I have now a way of looking at systems that is different from everything that I've been taught, right? And then we started, so these cellular automata, these neurosciences and nonlinear dynamics and biology and so on. We tried to put everything together. It was 900 pages, the first version. We went to the editorial, and the editorial said, you guys have to make it shorter. We didn't make it shorter. We made this a smaller letter and a bigger box for the pages. And eventually it turned out to be only 600 pages. So there it is. And it was, for me, it was a very important training. You can imagine. I was spending the summer just looking for self-similar stuff somewhere and making the figures. All the figures in the book are handmade or originally produced. So we spend a lot of time doing that. So, I mean, when we started also, now things are so different. We didn't have money until the 4th year of my PhD, I think. I didn't get any income for doing my PhD. I was teaching at the university, but I didn't get any grant. And we all made our PhDs with a computer, which was a 386 at the time. All of us were making the simulations there. And it was because the department was kind enough to give us one of their computers, right? So most of the time we were not in front of a computer. we were reading and making plots and trying to learn by heart what was there behind. So that was really a time that was very singular, very original, very mind-blowing, and that has very much marked what I've done afterwards. Okay, that was the other one. Okay, what is another of the important foundations? So chaos was one big area where we learned about nonlinear systems, and I think it's well into complexity. And the other is the statistical mechanics, and Marta has also mentioned it. That's essential because this was the theory that we had for interacting agents, right? And to see what are the emerging properties. These were systems where interactions perhaps were not as complex as in other systems like in economics or in social science, but this was the foundation of many of the methods we have, the tools we have, and the ways we have of looking at complex systems, right? So among other things, you have something which is very interesting in these systems, which is phase transitions. Right? The fact that you change a variable of the system in a continuous way, and you see a change of state in your system, this phase transition, is something that conceptually has been also very important in complex systems, because we are seeing these transitions in systems that apparently do not fall into this description of, say, gases or liquids, of description of matter, but they fall into the description of agents that interact and experience these transitions. If you Google phase transitions in biology, you can see that now we have examples of bacteria changing from one state to another collectively when you change some of the variables that control the system, and several other examples. Right, of course, those who have studied physics, of course, know who are the fathers of statistical mechanics. So these three persons here, and so the important point here, and I think that so this also has some links with what Marta said, many links actually. So is the fact that you can have a description of your system, this probabilistic. It's no longer deterministic. It's probabilistic, not because, so not in the same way that chaos has to be probabilistic because you have some uncertainty, but because you have these so many elements and you cannot measure, again, possibly all the properties of each of the elements interacting. So you go to statistics and you have some very nice descriptions of the distribution of speeds, for instance, in gases or in ensembles where at a certain temperature. And this is very closed and it's very nice, right? And it's also a foundation, again, of many other systems in the future. Still, from the beginnings of statistical mechanics to complexity, it was more than half a century to understand it as well when it appeared with Lorentz, Mandelbrot, Prigogine. We have mentioned these three people, Murray-Gell-Mann or Giorgio Parisi. Right? So it's an important step in the difficulty in describing the system from a mathematical viewpoint, but also from a conceptual viewpoint. There is new phenomenology in complex systems that was not in the previous systems. Something that I'm not going to refer to today is, for instance, this problem that Marta reminded me that when she was an undergrad, so she's significantly younger than I am. She attended a seminar of mine talking about synchronization. So this is one of the hot topics at the time. So how systems synchronize, in which ways they do synchronize, and how this leads to the emergence of collective patterns that can encode information or many other things, right? So you're not asking anything. I feel I'm going too fast through all this. No questions? No? Okay. Okay, another field that's an interesting one also, where people have been working in complexity is the evolution of language. You know, when Darwin wrote his famous book on evolution, then all of a sudden, evolution got extended to other areas. So it went into selection or into human selections as a precursor of what later had some difficulties, say. And also people started to talk about the evolution of language. So it was so controversial and the discussions were so hard that the Royal Society forbid discussions about the evolution of language until, can you guess, 1970. It was forbidden to talk about the evolution of language. Don't ask me why, I don't fully understand why. But so it was, I guess it was again the shock between people thinking about changing in significant ways nature and people thinking that nature was the way it was because it was given by a god, right? Or so made. Right? I guess this should be the difficulty. But yeah, so Murray Gell-Mann was very much in the evolution of language, and this is also a topic that I love. Okay, I'm not going to talk about the things I have made, but if you have interest, just go to my webpage and you see that it has gone through different areas so following somehow the path of complex systems in a way, always with evolution as a linking concept. So emergent properties, that's an idea that is essential to the idea of complex systems, right? Something that transcends individuals and interactions, something that you cannot deduce usually just by considering individuals and interactions, but that you either observe as an emergent property or you simulate in a sense, right? Let me give you a few examples and please ask or interrupt me if you want further explanations, right? A famous one is the rank size distribution of cities. I don't know if you are aware that since the beginning of the 21st century, so again, we're going back in time, very early in time. And I think I have another slide for that, but anyway. So some people were interested in measuring, in ordering a series of observation from the largest to the second largest, third largest, and so on. If these events were ordered and you were putting here the observable quantity, like it is in this case, size of cities, right? First, the largest city, second largest city, and so on, in many different regions of the world, it turns out that everywhere you see the same pattern. You see something that decays, that is compatible with a power law, in this case with an exponent -1, right? And that's puzzling. I mean, come on. I mean, everywhere in the world, you have different sort of cultures, idiosyncrasies, decisions about how you organize your cities, and still you come here and the distribution is the same wherever you go, right? So this calls for an explanation, doesn't it? I mean, if you're a physicist, you look at that and you say, wow, what's the mechanism behind? That's the idea, pattern and process, right? Same happens with the brain. Now we know much more about the brain, and we have lots of data. We are trying to exploit this data, but still the mechanisms are what's really hard. Sometimes when I see people working with this so data mining and they have lots of results about something, and then now we are going into the era of artificial intelligence, I wonder, well, just step for a moment back and think, what are you understanding of your system when you do this kind of analysis? I think that what Marta and Roger have done is something in between that allows you to quantify the data, and at least you see something that is not just a collection of numbers or correlations of matrices, and then you can go on top of that, and as they have done with some examples, right? You can look into the mechanism. You have to use what you know about physics, what you know about the system, and put your knowledge there if you want to make sense eventually of what is there, right? So for me, that would be an advice. So just don't get loose into data. So data is very nice, but we don't have to forget that we are looking, I think, that we are looking for mechanisms, for the principles behind what we observe. And this is now somehow the case of the brain and many other systems where we have much data, and some people are lost in the sea of data and have stopped thinking about what's behind that, right? This is also a real image. Well, I don't know. I think that this is heart tissue, right, in false color, when you see how So due to the electric interactions between cells, you have these emerging waves that actually make your heart pump your blood, right? And when this is broken, then you have all sorts of troubles, right? So these are emergent properties for some systems. There are many more, of course, and I hope you have found some of those also in the systems that you work with. And the other idea, and there was a question in the previous talk, is universality. That's an extremely powerful idea also that comes from physics of transitions, of phase transitions. And this is the existence of equivalent properties, emergent properties, in different systems. And this indicates that a few processes dominate the dynamics. Again, when one tries to make a model of some system and you're observing the dynamics, observing pattern formation, you have an extended system, whatever. There are, of course, two kinds of approaches that you can use. One is explanatory, the other is predictive. And they are usually different because in predictive models, it's fair that you put all sorts of variables, all sorts of parameters, as many of them as you like, in order to say something about the future of your system, right? The other is explanatory. And explanations come from adopting this statistical mechanics viewpoint. What you want to understand is the overall statistical properties of your system, not the future dynamics in a precise way, but these overall statistical properties. When you go for explanatory models, then these ideas like universality appear, because usually you have just a few variables that dominate your system, and you don't need to be exhaustive about every element and about every interaction in your system. If you work with biologists, for instance, as it has been my case for a long time, so they are obsessed with the details. And I understand, because they are mostly they mostly want to make predictions, right? So I've been studying for a long time virus evolution. And so people come and say, and what virus are you studying? I don't mind any virus. What do viruses? They replicate, they form heterogeneous communities, and they replicate with a high error, right, when they replicate their genomes. So since I'm looking for explanatory models, I don't mind what virus is there. I want to know what are the collective properties, the emergent properties, how they adapt, how they find new solutions, how they succeed in avoiding the effect of drugs and so on, right? But if you want to be specific, of course, you may want to know what's going the spike of COVID in the active site where it interacts with the human receptor, right? So these are different kinds of approaches. If you go for explanatory models, then universality is a very powerful idea, right? So those that have studied physics, I hope you have also studied or heard of, at least, I don't know how is it currently at the university, these universality classes that put into the same universality class many different systems which differ in the details, but that behaves collectively, at least near to critical points, in the same way. Right? This is important because there are just a few quantities, a few parameters that define the dynamics. So this universality might be guided by optimization principles, for instance. You want to be maximally efficient with minimum energy. And this is an example in how you distribute matter in 3 dimensions. For instance, your lungs, your circulatory system, for all animals, has the same properties because it has optimized it. So this way of branching in order to go to each and every cell in your body, but with a minimum expenditure of energy. Right? So then it turns out that it doesn't matter what system, which animal, which phyla you're looking at, the principles, the scaling principles are the same. Also, self-organization is involved in universality, and it has essentially the same basic idea of dissipating energy, right, in a way. So it minimizes or maximizes some quantity, and then you have formation of structures like these vortices that are found at very large scales and are essentially identical to the vortex that you find in your bathroom, in your bath tube when you when the water goes down, right? So it's an optimal way of doing something again. And well, this idea again that you have apparently similar systems that are quantitatively equivalent. Actually, this is the demographic density of London. And if you compare the properties of these systems, of this distribution, with a simple reaction diffusion system, it turns out to be the same. Right? So it's quantitatively, it's the same. Although here you have people, and there you have just inert particles. Right? So, all these ideas are there. So you see, there is you have some static patterns, you have some dynamics, and you have some interactions, and everything is mixed in this big box that we call complex systems. Also important are the effects of nonlinearities, right? Because, right, so the fact that you have nonlinear dynamics changes the outcome of your systems. It is important in this context that this idea is associated with the concept of threshold. The idea that you go over a certain quantity, a certain parameter, a certain measure, and you have a divergence in the behavior of your system. This can be a bifurcation in dynamical systems, right? You have a point where you either go north or south, or can be a state in your systems. You have, again, a change of state depending on the operation of this threshold, right? So this is well, an example where you have two different possible equilibrium states here. Depending on one parameter, you change into one state being stable, or the two of them being stable, and then through perturbations, you can make your system move from one side to the other. There are many, many examples of these systems, and an important one is, for instance, this North Atlantic current. Have you heard about it? Yeah, so this North Atlantic current essentially brings, so makes this water circulation that warms up all this area. If you stop this North Atlantic current, and there are models that have this threshold effect, separating circulation from non-circulation, you would have an H area, an ice age here, right? So because everything would get frozen, and it's also very important for biodiversity in the way it mixes warm and cold water and so on, right? So yeah, this is another kind of systems that are in the same group. Okay, so I have prepared also a few things to say about in which sense, a bit more specific about what's the relevance of spin glasses and what's the change of paradigm also that Parisi's work and others brought in these systems. If you have doubts, you can ask Marta afterwards, because she has actually worked on it. And I have just played around with a few systems, not that seriously, right? It's fun because when you read why Giorgio Parisi was awarded the Nobel Prize last year, so people knew very well what was the Manabe and Hasselmann Nobel Prize was climate, so everybody understood that, right? But once and again, when they were talking about Giorgio Parisi, I was hearing journalists saying, for the discovery of the interaction between disorder and fluctuations in physical systems from the atomic to the planetary scale. That was it. No one dared, actually, have you heard about that? I mean, nobody dared to explain what was that about. Right? Actually, it's not that simple if you have to convey this, the relevance of this prize to laymen, right? What's the time? Right. So how long was I supposed to be talking? At least.
1 hour and a half.
Okay, so there is a while still, right? So one of the important points, I think, in what Parisi did was the realization that complex systems can have multiple equilibrium states. The previous slide, I was talking about these two equilibrium states and the fact that you have bifurcations and you can have go from one state to another. But what happens if instead of having two, you have infinitely many possible equilibrium states? Right? This will be in an infinite system, but this is essentially what spin glasses do. Right? So since Marta also told a bit about that, you have this, so for systems with just two spins up and down, you have these periodically frozen configurations, and you have disordered states. But when you have these spin glasses, so you can visualize there is as the spins pointing in any direction, and well, they also have frustration. This is, I will explain this now. This leads to the fact that there are many configurations which are local equilibria, but are not global equilibria. And this opens a new phenomenology which has to do with aging of materials and with it has applications to many other systems, and I will give some examples later. Right? Well, I think that this is very basic, so I don't need to explain that in much detail. So for magnetic systems with these two spins up and down, you have essentially this transition to magnetization when you have many spins aligned in the same direction, or they are disordered, right? So you have here essentially at high temperature, you have all the spins pointing in random directions, and when you go to at the critical point, you have this emergence of long-range correlations, and when you are below the critical point, essentially you have an ordered system where you have magnetism, right? And you can freeze also these states, for instance, if you have a magnet. That's a system that is not frustrated, because if I have a spin up and all my neighbors point up, there is no problem in that. We can be all having the minimum energy, and this is possible at once for the whole system. But what happens when you have disorder? When you have disorder, you also have frustration. This is the example of parties or triangles, love triangles or friendship triangles, when you have someone who is a friend of you, but is not friend of a third person, and this other person can be your friend or not your friend, and this is a frustrated situation all of a sudden. And then if you go to a party and you have some friends and some foes, well, not foes maybe, but then you have to form groups, then here comes frustration. You see a group and you say, oh, there is my friend. Oh, but she's talking to, no, I better not go to the group. I'll wait until that person leaves and you go to another group and so on, right? So there is a frustration in the way you have to make groups if you are not friend of everyone. Friend of everyone or up spins, right? And changes and leads to these frustrated situations. What's the result of that? That there are so many different configurations that you can organize with people, for instance, when you have these frustrated interactions. And the same happens with spin glasses. You have these frustrated interactions, and then there are many different situations that you can arrange that are not minimal energy situations, because it is still you have some degree of you're not so comfortable, right? And this is the same that happens with spins, right? So this is, for example, an illustration of some of the properties that emerge when you have this frustration, which is, this is a representation of spins pointing in different directions. And then you have this phenomenon of aging, right? Because somehow the system is trying to accommodate to situations that are not that frustrated, since you are working at a finite temperature, you have some changes, some flips of spins and so on, and then your system is somehow aging, because you see that the situation in which it was prepared takes a long time to fall into attractors which are more stable, but are not readily accessible. Right? So this is a visualization of how this phase space might look like. This is the same graph landscape that Marta was showing in her presentation. If you're at a very high energy, then you somehow don't see the details, and you are exploring all of your phase space, like in this picture here. But if you lower the energy, you start to get trapped. Depending on what was your initial condition, you get trapped into different wells in your phase space. And once you fall in a well, it requires some energy to jump to the other well, right? So in this process of looking for the minimum energy well, you have this aging, and you have a self-similarity of times and of scales that come one after another when you jump from small wells to neighboring small wells. But if you want to go to a well which has a higher energetic barrier, then it takes longer, right? But you have this kind of ordering that is very nicely seen in granular matter systems. This is a very typical example of many attractors and of of how you can freeze a configuration depending on the initial condition, right? If you have a box of balls of different radius, you have many ways of packing the balls. Yeah, you start, but if, for instance, you take and shake your box, you are increasing the energy of this box, increasing the temperature, giving some energy. You can have, for instance, that you go into configurations which are more optimal than the initial when you started. But in the absence of temperature, in the absence of energy, you would remain here, right? So this has consequences in that when you study these systems, you are usually not seeing the complete properties of your system. That is, if I prepare my system and I freeze my system and I want to make some measures and I'm not aware that I have to study different replicas, different configurations, I will obtain results which are very misleading, right? And there are many systems where this happens, and one of those systems is economics. So Marta mentioned computing, so computers, but what Parisi saw of these systems with many minima and how these minima are organized and how the system goes from one part of the phase space to the other, this has application in many systems and is a change of paradigm. Because we were more used in to think about global attractors, about unique solutions, and about ergodic systems. And these systems are not ergodic. So I'll give you an example later. So again, instead of looking at the determinism of these systems, we have to look at the probability that a certain configuration appears, right? We have to do some averaging, some sampling in this space of possibilities, right? We cannot control the interactions, we cannot control the variables, and then the description of my systems becomes necessarily probabilistic, right? Still, there might be some convergence, some subset of things that are possible and some things that are not possible. I recall the example of weather and climate. I cannot predict weather, but I can say something about climate. So not everything is possible in climate. There is a convergence of the different solutions to a whole that is not that, say, difficult to predict. So not everything is possible, right? That's the message. Right? So this is an example of what could happen in biological evolution. This is a draw by Ricard Solé, by the way. So at early times of life on Earth, we had these fauna, which were ediacarans. This is previous to the Cambrian explosion. And there was very simple organisms with soft bodies. And the question is, what can emerge afterwards? Is everything possible when you have transitions to other organisms, to other plants? Well, not everything is possible. For instance, predation was probably a sort of a need that had to emerge in those systems. And then there are some restrictions also to symmetry and to ecological relationships and so on. So probably not everything is possible. If you wonder about these things, there is this nice book, La Logic of Monsters, where you can find how there is this convergence despite the apparent sensitivity and the difficulty in replaying the tape of life in this case, which is like replaying any other experiment that you may have run at any time. Okay, I can't resist and bringing as example the COVID pandemic, right? As an example of complex systems, because it has all the ingredients that we've been talking about. Many agents, interactions, spreading, uncertainty, heterogeneity, all at once, right? Bad data, also, I have to say. So this is data for the first wave in Spain, right? And well, of course, we know that there are many different processes going on when you have propagation, and one important one is the heterogeneity in propagation, right? Still, most of many people describing these systems, not the ones that were somehow expert in epidemics, but many people who work with the differential equations just took the very well-known SIR model, right? And you can try and feed your data. That's easy to do. And actually, If you take, I've just rescaled the data and put the curves for the SIR model that are in the Wikipedia. I haven't even attempted to fit, right? And you see how well it describes the curve, right? That's amazing, isn't it? So this made many people believe that they could actually predict what would be going on with the pandemic. Because you take 3 differential equations, and look, wow, that's amazing, right? Well, it turns out that it's not so easy, because this only works in the assumptions of the system. That's another very important point. Some people make models, and those models have assumptions. If you are out of the assumptions of the model cannot be applied, right? So the SIR model can only be applied in a situation when you exhaust the number of susceptible in your system. So you infect all possible susceptible individuals, and then of course you have a relaxation of your system because the epidemic stops because there are no more individuals to be infected. This was not the situation here. Actually, the fraction of population that was infected was well below the full amount of available susceptibles, right? So these systems actually do have at least one bifurcation point, right? And in this bifurcation point, what happens is that if you just modify slightly the model, and this was something that we did by including a class of confined people. Because confined people are people susceptible that are not exposed to the virus as long as they remain confined. Right? Okay. So then what happens here is that you have a future of possible situations, right? Even if your curve is bending, as you see here, you may go to a different regime of propagation at a different speed, or you may have a full wave with so that decays at a certain time. But when people were making predictions about what's going to happen, they were using the SIR model in many cases, not all, I insist, but in many cases, and they were going to the news. And you could see some predictions of when we will have the peak, when this is going to end, and so on, using models that were not suitable to describe that situation. So actually there was a certain probability of reaching the peak, and if you didn't have the peak, you would have continued to higher, the propagation wouldn't have been stopped, right? So what we have in these systems is something that is similar to chaos. Chaos has sensitivity to initial conditions, and these systems have sensitivity to parameter values. Even if you fit your initial curves, of course, you have a certain range of variation in the parameters you fit. And when you consider this range, the universe of possible trajectories opens like a funnel. So this is something that we worked in at the beginning of the pandemic, and we had also a paper in Quanta magazine, a very nice one, so explaining why you cannot predict. This is like weather. This sensitivity to parameter value is the same sensitivity to initial conditions that you see, and there is an horizon beyond which you cannot predict, like in weather. The question is, do we have a climate science for epidemics? Can we say something in the long term that is not this short term where we know that we cannot predict? That's an open question. And I wish the governments would invest as much in epidemics as they have invested in predicting the weather, right? And then we could be one step further. Okay, here I have made a comparison between these two situations, and actually the situation with epidemics is much worse than with weather, you see, because it has been of interest since long. The data in weather is precise, abundant, distributed, and shared. So no one hesitates to say, no, I have this temperature of this wind or this what, but everyone hesitates to say, I have this number of infected, I have detected new cases, I have a mutation, right? So this was not, data in epidemiology were poor, inconsistent, low resolution, and not taking the same way everywhere. Models for weather, again, you have complex, global, multi-level, tested against predictions, open, blah, blah. Here we have, with some exceptions, very simple models. There are also agent-based models, but they suffer the same problems with predictability that these SIR models, right? You have some origin of unpredictability in chaos or in the fact that this is an exponential process. So contagion propagation is controlled by exponential dynamics. And there you have the same divergence that you have for chaos. The situation is much worse because weather is agent independent, right? So it doesn't matter if I want the weekend to be sunny, but for epidemics is strongly age independent. So the actions of individuals, which often come as a response to the information they get about the current state of the system, how many people are infected and so on, do determine the responses. And this again feeds back into the system. And this is very similar in this way to economics, right? Because you have, if you say this company is going to crash, you have everyone selling actions, right? So, and then there is a feedback that is makes situation worse in epidemiology again. And then we have this predictability threshold, which is about 1 week for weather, and we don't know what's the threshold for epidemiology. For sure, we can say some things a few days from present, but I wonder how far. Right? Well, okay, we made some popular science comics also during the pandemic to try to illustrate the fact that predicting the behavior of the population is sort of impossible, right? And this affects the dynamics of the system. Okay, let me give you an example with econophysics of the difficulties. This is related to the Parisi's contributions, to spin glasses, and to some of the properties of these systems. Here I'm showing you a time series of, I don't know what the price of money or something or whatever. This is something that has to do with the price of selling something. You can construct some simple models where you have this kind of spikes. And so the spikes repeat at certain intervals. This is half deterministic, half probabilistic, right? So you have these resets that occur at some points when your system breaks down. This can be a series of successful events, right? Where something increases the price, and then you have some crashes. These systems have the property of being non-self-averaging. What does this mean? This means that I can calculate, like in this graph here, the green curves are the analytical solutions to the system. So the average properties of the system in this case. And the blue, the black curves are numerical realizations of the process, averaged over 1 million realizations. And you see how far it is from the average. This is a property of systems where the dynamics have a power law distribution, statistics, power laws with fat tails, where the dynamics are typically controlled by extreme events. So the dynamics in those processes are controlled by these very large events, which are very rare and occur, well, at points in time where we cannot predict. Right? So, but you see what happens here. This is an average over 1 million realizations. You have the average here. This is the analytical calculations, and you see that it diverges severely from that. So I don't have much experience in economics, but I know that people still use descriptions of the variables which are based on the assumption that they are Gaussian distributed, right? If you take Gaussian distributed variables, then of course the moments of your distribution, the average value, the second moment, and also the skewness, which is often used as a predictor for, so when you have to invest or something, volatility, right? That's the word in economics, right? Yeah.
If you sample from a distribution that has any variance, you will recover the
Exactly. Exactly. That's it. Yeah, but many accepted truths in economics come from the assumption that the variables are Gaussian distributed. So if you use the third moment typically as a definition of volatility, which is an economical concept, then of course your predictions are very bad, right? Because the distribution is very different. Yes. right?
Have to have a partial like sampling of your system, and then these things happen too. Well, I'm just saying another case in which this could happen.
Of course, yeah. This is a demonstration of, I may repeat, of non-ergodicity of the system. But in this case, even we had, so averaging of the replicas, if you want, because we have made different runs of the system and still you have this non-convergence to average values. That's a change of paradigm again. So everybody thinks that if you have a large enough set of data and you take the average and the moments of your data, this is telling something about the process. But it turns out the same description of the process that you can solve analytically and you can simulate numerically do not coincide. And you need other descriptors, you need other observables for your system. This is important to keep in mind, right? And this happens when you have these complex phase spaces full of separated attractors, right? Okay, I think I will be finishing because I just had some examples of social sciences as complex systems. Again, you have many other cases. So you have the distributions of incomes. For many people follow Maxwell-Boltzmann distribution, but the wealthy majority follows a Pareto law, which is actually this law like in the distribution of city sizes. You have then pattern formation in communities of ants and humans, which are very similar, right, in the way they construct paths. That's, I found it always amazing, right, that we believe we are so intelligent, we plan everything, and we behave as our individual decisions and so on. And as a collectivity, we are so similar to ants or to any other animal in our organization, in our large pattern organization. So I find it very interesting, right? Yeah, and these are also some other examples. For instance, that's a nice one. This is the distribution of languages in the world, of different languages, about the 6,000 actual languages in the world. And when you calculate the statistics of this distribution of languages, it mimics exactly the biodiversity distribution. So you have lots of biodiversity at the equator, lots of different languages at the equator, and it decreases as you go to the poles, as you go north and south. And if you calculate the ranges where, so the areas where a language is spoken and the number of people that speak a language, and you calculate the species area population, like in ecology, is exactly the same distribution. So we as a collective, so our diversification in languages is the same than biodiversity distributions, right? Okay, let me finish with a sentence, and I will ask you which year is this sentence from, right? It says, at first sight, the facts of human life do not seem to subordinate themselves, as do the phenomena of nature, to certain general laws. Statistics show, however, that this is only a difference of degree due to the more complicated nature of human relationships. And we just have to learn to read the statistics correctly to draw more general conclusions. And it's not unusual to find interesting and strange laws. This sounds to me very modern, like complex systems in social systems, somehow. Yeah. Again?
Late 19th century.
19th century. Late probably, yeah. Yeah, what from? 1913, right? So well before any new complex systems ideas, there were a large group of people, among which Zipf and the principle of least effort was describing much of human patterns, saying that we were essentially lazy, right? So this is a minimization of energy, a minimization of effort, and this leads to patterns in social sciences that are the same patterns that we see in other complex systems, right? And this is different systems that have still the same statistics, right? So I think I will close with that. I had the last slide because I've said that I prepared this talk for this for a cycle on Nobel prizes, but that was actually a history of complex systems. And it's interesting what they said, right, about why the Nobel Committee was awarding this prize in complex systems. So the modeling of climate, and there Parisi was a sort of the obscure person making sense of this complexity of this new paradigm is solidly based on physical theory and robust results. And this was a message that the Nobel Committee wanted to transmit. But I think that for us as a community, there is this other message, right? So complex systems is a theory that has sound principles, and this is sound science. This doesn't make much sense to you, but I've been going through much skepticism in how we were dealing with problems which were not pure, hard theoretical physics. So for me, it's 30 years after I started in the field, it's really an achievement that we are at this position. And I hope that your future is lighter than mine was, although I had much fun. Okay, so that was it. Thank you.